So what we're going to quickly have a look at is another way to represent numbers in terms of index notation, what it actually represents, but then we're also going to relate it back to the previous video of expanded notation, how we can actually represent index notation using expanded notation and how that relates to the powers of 10. So, first of all, what is index notation? Well, this is an example of index notation. We have a larger number, in this case the 5, and a smaller number in the 3 that's up to the right of the 5. Now, the big number 5 we call the base of our number, all right? And it's what we're going to multiply by itself. The power, all right, or the little number 3, we can refer to that as a power or an indice or an exponent. It tells us how much we're going to multiply this big number by itself. How many times, I should say. So in this case, we're going to multiply the big number 5 by itself 3 times. So what we'll get is 5 times 5 times 5. And of course, we can multiply those 3 together and we'll get 125 when we do so. All right. So essentially, we have two forms that we can represent numbers in. We can have it in index form, such as the 4 to the power of 3. All right, we can have an expanded form, such as the 4 times 4 times 4. All right, so we've got these two kind of forms, and we can move between both of them. So, for example, if I wanted 4 to the power of 7 in expanded form, this is going to be equal to 4 times by itself 7 times. So it'll be 4 times 4 times 4 times 4 times 4 times 4, and what I'm up to, 6. So one more time, which is 7. So you can immediately see already that the index notation is a lot nicer to write out that bit of mathematics, that multiplication out, because it's not quite so long. But we can continue doing it. So 2 to the power of 5 is going to be the 2 times 2 times 2 times 2 times 2. And once again, that's going to take a lot longer to have to write down than the multiplication of, 2 to the power of 5. So the reason why we have index notation often is it's simpler to represent calculations that we need to make. So we need to also be able to represent something that is in expanded form back into index form. So for example, we've got this 3 times 3 times 3 times 3 times 3 times 3. So our base here will have to be the 3 because that's what's multiplying by itself. And our power will have to be 6 because our base is multiplying by itself a total of 6 times. In our example here, we've got 6 that's multiplying by itself 3 times. So our base will need to be our 6, that's the big number. And then our index will need to be, or our power needs to be the 3 because that's how many times 6 is multiplying by itself. Now, you might ask yourself, well, how does this actually relate to what we were doing in that previous video? Well, let's come back to our place value system. Our place value system can actually be represented in terms of powers of 10. So, for example, let's take the tens column. We'll talk about the units afterwards, but let's take the tens column. If we think about 10 as itself, if we just have the number 10, that's what 10 is. So this is 10 to the power of 1. 10 times itself 1 time, I guess. You can think about it like that. All right. In terms of 100, though, we can actually break 100 down as 10 times 10. All right, because 10 times 10 is 100. So this ends up being 10 to the power of 2. Oops, let me quickly go back. All right, we can keep going with that. So if we've got 100, if we times 100 by 10, we'll actually get 1,000. So this will be 10 to the power of 3 because this is going to be 10 times 10 times 10. 10 times 10 being 100, times that by another 10 is 1,000. And this actually keeps going. So 10,000s will be 10 to the power of 4. 100,000s will be 10 to the power of 5. Millions will be 10 to the power of 6. 10 millions will be 10 to the power of 7. Which brings us to these little fellas down here, the units. All right, now I'm not going to get into why it occurs in this particular video. I do have a video on why is anything to the power of 0 always equal to 1 if you want to look at the reason to why it does. But we can actually represent the units as 10 to the power of 0. Now, the reason for that, like I sort of alluded to, is 10 to the power of 0 is equal to 1. All right, because anything raised to the power of 0 except for 0 is always equal to 1. I have a video on that. It's sort of a Year 9 topic. So if you want to go into the Year 9 section of my website, you can certainly have a look at that. But for now, let's just accept that 10 to the power of 0 is equal to 1. And it kind of fits this neat little pattern we've got happening here as well. Okay, so how does this relate to what we were doing in that last video? Well, we were being asked to break down numbers into expanded notation. We can also actually break them down into something that's known as expanded index notation. Now, if you think about expanded notation, that was breaking a number down into its individual digits, being the sum of its parts. We're going to break those parts down. So let's look at the 365, for example. We could break that down to be 3 of our hundreds, plus 6 of our tens, plus 5 of our units. Oops, that should be a plus symbol there. Let's get the little eraser out. So that should be a plus 5 of our units. All right. However, we can represent, if you think about 100, all right, we can represent the hundreds with 10 to the power of 2. So we can actually represent this as being 3 lots of our 10 to the power of 2. All right. We can represent the tens as 10 to the power of 1. All right, so this is going to be plus 6 lots of our 10 to the power of 1. Now, what's unique about the power of 1? We don't have to write this power of 1. In fact, it's actually better or considered to be more appropriate to not write it without the power of 1 because we just assumed that that's going to be the power of 1 if there's no power written. All right. And then we've got 5 of our units. Now, obviously, our units is represented by 10 to the power of 0. So this is going to be 5 times 10 to the power of 0. All right. And what we've just done here is we've broken this up into the sum of its parts, but now we've actually represented its parts in index notation. So let's have a look at another example. So this next one, we've got 1,302. So the 1,000 will be 1 times 1,000. The 3 will be 3 times 100. And the 0, we've got 0 tens, but we've got 2 units. So we've got 2 times our 1. Now, 1,000, if we look at the previous slide, 1,000 is going to be 10 to the power of 3. All right, so when we look at this, this is going to be 1 times 10 to the power of 3, plus our hundreds. Our hundreds is 10 to the power of 2, so this is 3 times 10 to the power of 2. And then our units is 10 to the power of 0, so this is 2 times 10 to the power of 0. Let's go one more example. So here we've got 10,053. So the 1 at the start is our 10,000s column. So this will be 1 times 10,000. We've got a couple of zeros. So the 5 is in our hundreds. No, sorry, our hundreds, our tens column. So this is going to be 5 times 10. And then our 3 is in our units column. So this is 3 times 1. Now, 10,000, if we have a quick look-see on here, our 10,000s column is 10 to the power of 4. So when we write that in index notation, this will be 1 times 10 to the power of 4. Our 10 is just 10 to the power of 1, or just 10. So this will be plus 5 times 10. Then our units is 10 to the power of 0. Hang on. Plus 10 to the power, oops, I should have the 3 in there. So 3 times 10 to the power of 0. And essentially that's how we can use index notation in terms of using the powers of 10 to break numbers down into expanded notation or expanded index notation as a whole.